Alright, welcome to the Midterm 1 review. Let's review as much as we can. Definitely go back to the previous lectures, of course, but I'll do my best to give you the most bang for your buck here. So yeah, let's talk about data representation to start. So we have stuff and we store that stuff inside of our programs. Pointers, for example, that's a big thing that we care about storing, is on our machine, on our 64-bit ARM processor, every pointer takes up 64 bits, or 8 bytes, so that lets you have a lot of RAM, potentially, one day. And because we need to store 64-bit addresses all the time, that's kind of telling us how big our register should be as well. Every pointer and register in this class is 64 bits long, and that's pretty much the common thing these days, 8 bytes total. Okay? Every integer is only 4 bytes long, 32 bits. So if I gave you an array of integers and I told you that, like, this is the array 1, 2, 3, it starts at address 100, that's the address of the 1 element, you could immediately tell me, right, the address of the 2 element and the 3 element. They must be 104 and 108, right? Because they take up 4 bytes each. And then strings are made up of characters, and each char is a 1 byte thing. Okay, so yeah, we used a lot of C strings in particular in this class, like when we're talking about command line arguments, your char star argv bracket bracket. That was an array of C strings, special char pointers to the start of an array of characters, but they ended with that special null terminator character. So for example, like the string hello would be represented like this as a C string. You got the H character, E, L, L, O, and then the null terminator. So that's a C string. Okay, so if this started at address 200, you can tell me what are the addresses of all these other characters, couldn't you? This has got to be 201, 202, 203. Forgot the O, 204, and then 205 is that special null terminator character that tells you when everything's over. Okay, and so that's what you get when you say .ASCII or ASCII's hello in assembly in like the data section. So that gives you that, and that's what the Z stands for. It's going to give you that null terminator character. Okay, if you just wanted an array of characters, you could do it with ASCII. Okay, or if you're going to use non-C library things like syscalls, they don't care as much. So if you did instead ASCII hello, that just makes an array of characters, and it ends where on the last character, so that would only give you up to here. That would be what ASCII hello does. But this is ASCII's hello. It gives you that null terminator right at the end there. And if you want to access a single byte value of like a string, you have to do load byte and store byte into a W register, huh? Load byte and store byte. Without the B's, you're able to load and store into 4 or 8 byte registers, right? W registers or normal big X registers. You could read 8 bytes or 4 bytes at a time, but the B reads a single byte into a W register still, though. So it's kind of wasteful, but that's as small as it gets in our register land. So yeah, I think that's all I wanted to say about data representation. So yeah, every register is 64 bits long. Pieces of those registers are your W registers as well. Okay, if you zoom into this pretty picture, it says all that fun stuff. So those are 64-bit, 32-bit. If you say W instead of X, do remember the rules. All right, remember the rules for which are your scratch registers, which are the ones that are safe between function calls. All right, so X0 through X18. Those are all getting clobbered, all right? Whenever you call a function, you say BL printf, for example, printf. Not only does that set this fancy place LR, which is the address that it should return to, BL printf. This sets LR, don't forget that. That's your link register. Sets LR. Not only does it do that, it also, and it tells LR, like, point to the address of the instruction right after that. Not only does it do that, but printf itself, like the code for printf or whatever function you're calling, is, well, you probably clobbered your own registers by setting the parameters to printf, and then it's allowed to use all these bad boys to call its own functions and like do its scratch work, whatever it needs to do to actually print that thing. All right, or to execute whatever function you're trying to call. So yeah, anytime you call a function, all these registers are allowed to be clobbered, if you would like things to stick around in between function calls, everybody's agreed to keep x19 through x28, I'll zoom in there, nice and safe. Those are your saved registers. Nobody's clobbering those. They're always going to get restored later, and we promise to do that too if we ever touch them. And yeah, you could save them there, or you could also use the stack, right? Use stack memory, because that just grows and shrinks, and nobody's touching anybody else's, all right? So yeah, put a lot of your stuff that needs to be saved across function calls into those registers or on the stack. Remember, to put something on the stack, you got to make room using SP. SP is the address at the top of that stack. It's a special register, and to make room, you subtract from SP. So you'd be like sub SP, SP. It's always got to be a multiple of 16, remember that. Multiple of 16. Multiple of 16, don't forget. And if you want to like make your own function calls, you have to save your own LR, for example, with like a store LR somewhere into SP. For example there, okay? That's what we've been doing. And you got to clean up after, before you end the function that you're currently in as well. So yeah, that's most of the registers I want to talk about. The last one is PC. PC is a special register. It is short for, if I zoom in again, short for the program counter. It's the address of your current instruction that's running right now in the CPU, because it lives in memory and it has its own little address. So yeah, every time, for example, when you say blprintf, it's going to set LR in the hopes that it eventually, like when you say ret, it'll jump to there. All right. But yeah, that's the goal. When you say ret, you have something in LR. That's the place you need to return to. That's going to set PC and change which instruction you're going to execute. It's not the one right after anymore. Same with branching instructions. It sets PC to something that would have been different than the normal thing. Okay, unless it falls through, of course. So yeah, that's registers in a nutshell. This is a very important picture to always keep coming back to remember your stuff. But I think we're ready for like a hello world now. So let's do a couple hello worlds. All right. So we learned the C language. That's slightly different than C++. You have to use standard io.h and all that. So let's do a hello world in C just to remember everything. I'll call it hello underscore C.C. Give myself some more room here. So we got include, not iostream, but standard io.h, and normal main function with a return 0 as usual. But it's printf, right? That's your standard printing function in C. So we'll just say hello world and a new line, and that'll be the program. Compile with GCC, hello C -o hello C, I guess. And bam, we got our hello world. Nice. Okay. Let's also do it every other way. Let's make a from scratch, not using the C standard library, assembly program with an underscore start rather than a main. This is not using libc at all. We'll do a write syscall, and then we have to use an exit syscall always to end the program, all right, with a certain return code. So yeah, we'll have to consult our handy-dandy list of syscall numbers. So we're ARM64, sort, yeah, so read and write, those are here, 63 and 64, so we're going to use write, click on that, and they're also going to exit, so that's 93, okay? So yeah, let's use both of these to our advantage. Yeah, remember that when you're making a syscall, let's pick on write for a second. When you're making a syscall, you got to put in x8, the number of that syscall. So write was number 64, and then you give all the parameters in x0 and onwards. All right, so unless it's an int that it wants in that position, then you put it in the W register. So it's an int file descriptor that we would like to write to, and we're going to write to a special file that is the standard out. So we're going to put 1 in W0, right, because it's a 32-bit value. You get those 3 special files are always open for you. They're not really files, but they correspond to things, special secret things like standard input, that's the user's keyboard, that's file number 0. Standard output is file number 1, and then there's also the standard error output, secret file number 2. They're not really files, but write knows how to write to things that are like files, and this is good enough for it. All right, so we're gonna give 1 to W0, and then you put the starting address of the string that you'd like to be printing, or writing to this secret file. Here, that goes in x1. There's got to be a pointer, right? So we'll put the string there, and then you put how many bytes you'd like to take from this string and write into this file. All right. So we want to take the size of our string that we want to print out, and that goes into x2, because this can be a very large size potentially, more than 32 bits. And then once you have your syscall set up, you say svc number 0, that's supervisor call, right? And that tells the operating system to take over. We're ready for you. Do this thing that I asked you to do. All right. So let's do that. And I guess we'll do it from scratch. Why not? So we're going to do hello_start .s. Oops. Sorry, I want to edit a file called that. There. And so it's global start, so that the assembler can see it, and then we give our start label, and here's where it begins. And then we want to do a write syscall to print hello world, and then we also would like to exit with a 0 return code. All right. So there's that. I'm going to be printing hello world, so I need that in the data section as a string. So call it str, and the write syscall just wants an array of characters. It does not know anything about C strings. This is not C. Sorry, this is not the C standard library. This is also not C right now, I guess. It is assembly. So let's put our string, new line, and how many characters are these? Remember that the new line character is a single character. That's going to be 14 characters total. All right, so let's set up the write syscall now. So move into x8, 64. Let's just copy this, make it easier on me. Whee! I don't know. I don't like the uppercase though. Let's fix that. It bothers me. Okay, so we got that one. We did call it stir, and then the size I said was 14, I think. Cool. So yeah, that'll print it, and then we don't want to just fall through and start running the string as an assembly instruction. We would like to exit gracefully, and so we need to exit with a 0 return code. That's the exit syscall. It's syscall number 93, and it takes one argument, so that's going in W0 because it's an int, and that's the status code, the exit code that we want to give back. Okay, so let's do that. So I'll steal most of this. So we have nothing in x1 and x2. It's going to be 93, and we want to exit with a 0 return code. All right. And then, yeah, remember that this svc0 is the part that actually performs the syscall. That lets the operating system take over and do the things. All right. So this is not a C program, so there's no start function. There's no main function. Sorry. There's a start label, and so we have to assemble it and link it manually. -o hello_start .o ld hello start .o -o final executable file without any extensions. And if I did it right, and I didn't, oops, this needed to be hello world. What did I do wrong? How'd that get to be n? I must have done something weird, sorry. But yeah, you need that string to be there for sure. Let's reassemble. Relink. Rerun. There we go, that's better. Cool. So yeah, it works every time. It's not segfaulting, and yeah, so we're just asking the operating system very nicely to write a string to the terminal, and that's the standard output, as well as exit with a 0 return code, which you can check. That's the $? Oh, well, you gotta run it. It's about the previous run of the program. There it is. All right, so that's that one. And then finally, let's do one in assembly with main and a call to printf, so we can just compile that with GCC once we get that one working. So let's do that. I'll call that, I don't know, hello_main dot still.s. And I did it again. There we go. So, all right, now we have a main function. So it's .global main, and then we say type main is a function. So anybody who wants to know knows. It's for the C compiler, I guess. And then you can start with main. Okay. So we are going to be calling printf. So I better save LR on the stack. So sub SP16. Always got to be a multiple of 16, and then I'll store, store LR at just wherever SP is pointing to now. That's a brand new place. It'll take up those 8 bytes. All right. And so that's nice and saved. And then once I'm done with everything, I'd like to restore my stack. All right. So restore my stack and then also LR. So I'm gonna load into LR or whatever is at SP right now, and then I'll add to clean up my stack. All right. And then I will I'll then go and return 0. All right. So this will be like clean up stack and restore LR because it will get clobbered by the printf call, and then let's return 0. All right, so we would like to put into W0 the number 0 and ret. Perfect. All right, so now it's time to print. So we're gonna like make a string. You can steal it from the other one, right? Mostly steal it. And so we kind of just want to say printf of the str, right, of that string. That's like what we'd like to do. So first of all, this has got to be a C string because this is the C library we're calling, ASCII Z this time. And yeah, when you're calling a function, you got to put your first argument in x0. All right, the first in general, right? The first 8 arguments go in x0 through x7. Remember that rule. Everything else goes on the stack in reverse order. So yeah, we're good to put just the string itself, which is called str, into x0, and then we'll just bl printf, and that's going to clobber LR, and that's why we had to save our old one, because it's going to move into LR the address of this instruction, right? Because that's where printf needs to return back to. We needed to save where main itself needed to return back to, up here. And that's why we got to clean it up and restore down here later. Okay, so yeah, those are the relevant pieces of code, and we'll compile this with GCC because it needs to link the C library and all that. Cool. Yay, it's working, and it is correctly returning 0. Nice. So yeah, remember that ret is just going to jump to whatever's in LR, which is what we restore, and that's the return address that main needs to go back to. This jumps to the return address of main, which is maybe like underscore start, like that's being inserted by the compiler still. That's where we go back to, and then it's going to eventually make the exit syscall. All right, so there's that. What else do I want to talk about? Let's just do more general assembly things. Let's do some like arithmetic, comparing things and branching based on those comparisons, and then looping as well. So let's just do a fancy example where we let's sum all the numbers from 1 to 10, and then we'll use that sum as the exit code of the program, because why not? Okay, because why not? Let's do it like that. So I'll just make a new file, and let's keep it outside of the C standard library. Let's just do an underscore start kind of assembly file. So I'll keep this one. And arithmetic.s is what I'll call it, I guess. And so we won't be writing anything, so we don't need the data section. We still need to exit 0, but not 0 anymore. We're gonna exit with a different value, but that value needs to go in a W register, so that's where we need to work. All right, so let's put into W0 the return code that we want to exit with. That's where it needs to go anyway. All right, so what we're gonna do, right? So we'll sum 1 to 10 into W0. Okay, because that's what I want to do in this example. So let's, I guess, start off the sum in W0 at 0. That's good. And then we need another register to like keep track of what number we're on. Let's kind of do it like this. We'll do 4, like let's use W1, start it at 1, as long as it's like less than or equal to 10. We're good, because those are the numbers we want to add in, right? and then like W1 plus plus. So let's, I guess we got to start W1 at 1. Move W1, move into that, the number 1, and then now it's time to loop. All right, so what does my loop need to do? It needs to always compare, check and see if this W1 value is a good one that I still want to continue with, and then run the body and then increment. All right, so compare, got to compare now. W1 with 10, I guess, and if it is any greater than that, if it's 11 or bigger, so if it's the opposite, right, the opposite of less than or equal to is greater than, so if it's greater than, I'm done. Otherwise, I want to keep going. So BGT, call it done, and I'll put the done label down here. We're not executing with any special return code anymore, because we're putting it in W0. So there's that, and yeah, if we're still here, right, remember this is branching, right? Branch based on the comparison that we just did. And this is branch if strictly greater than. That's how you read that. And yeah, what do I want to do? It's like, well, I want to add into W0, right? I want to do like a W0 equals itself plus W1. And then I need to do this W1 plus plus line. And then I need to continue the loop to the next iteration. All right, so something like that. So let's fill these in. So add into W0, W0, and W1. Add into W1 itself plus 1. And go back to the loop, so BAL, or just B. B loop, all right? That's shorthand for branch always, okay? So we always come back, check our condition. Eventually, it will be too big, and we will branch away and end our program, and we're putting the right answer in W0, so that's what the exit syscall is going to see. Value NW will be our exit code. So yeah, that should do it. I think that's all that I wanted to show in that example. Let's see if I can give you most of this file at once. Looks like I kind of can. Perfect. So let's assemble with AS and link with LD. We'll call it arithmetic.o, LD arithmetic.o into a file just called arithmetic. And we'll run it, and the sum of all the numbers from 1 to 10 is 55, so that seems right. Cool. So yeah, I think that's what I wanted to do for that one. Let's also talk about the counterpart, right, of the write syscall, the read syscall. We'll do that. Oh, and I think just to spell out the kinds of branching that you can do, I think I should say that before we go there. So like, it's always B dot something, right? B dot, what do you want to branch based on? Your comparison. So like you could do branch if the things were equal, branch if the things were not equal, branch if they were less than or equal, all those things, right? Branch if they were strictly less than, and everything under the sun. So I had a table that I gave to you in one set of slides somewhere. Go back to that one, okay? So yeah, that's what branching is good for. Let's also have an example of the read syscall. Let's do like part of that initials example that I did in class before. Let's do that, and this is the read syscall. So it's syscall number 63, and it works very similar to write. So, oops, I wanted that to stay open. So let's gotta resort it, I guess. Gammon. We have a read syscall where 63. There it is. So if you compare this to write, it's very similar. So which file do you want to read from this time? So we're going to read from the standard input. So 0. 0 is going in W0 because it's an int. And then where do we want to put what we read? Okay, so you have to give the address of a string to fill in this time. All right, address of a string we want to fill in. And then how many bytes do we want to read from this file, the secret file that is the user's keyboard this time, okay? So that's gonna stop the program, have the user type some stuff, hit enter. It'll take that many bytes that we put next to that they entered from their keyboard input, and then it'll store that as a string in the memory starting at where we give an x1. Okay, so yeah, let's do that initials example, or a lot of it, all over again. So steal a lot of this, and I'll say, let's see here, I'll call it just read.s maybe, that'll work. And so let's clean this up, because I do want to just like exit 0 again. So let's do move w0, 0. That's perfect. So now we have a clean slate. All right. I would like to read. I want to get the user's initials. Let's get 3 characters from the user with the read syscall. All right. That's what I'd like to do. Really though, when you use read, you're getting the enter that they press as well. So you're getting that new line. So if you want to read 3 things, 3 concrete things, you need space for 4 things because you're going to get that enter as well. So really 4 characters total, because we have to, like, we've got to eat it up. We got to eat up the new line character so that the next read doesn't see it. Right? We have to eat up the new line character. That's the technical term, I guess. So yeah, let's do the read syscall. So move into x8, 63, and then it's going to be move into w0, 0. That's the standard input. And then we would like to read into a place in memory, so let's make some room in the data section. You could also use your stack. But here, let's make some room for 4 bytes, right? Because we're going to read 4 bytes. We'll just start them off with 4 x's. We'll go into there. Load into x1, the address of the string, so that's what I want to fill in, and I want to fill in 4 bytes. Take 4 bytes out of this file, which is the user's keyboard, and then store them there. All right, so we're going to get their initials and then a new line after all that. All right, so SWI0, or sorry, SVC0, excuse me, goes and runs the syscall, and that's going to make it all happen. All right. And then, just for fun, let's just write out what we just read. So we'll use the write syscall as well. Write what we just read. And so let me go steal that from the other file. There's that one. So we would like to write, it is still called stir, but there's only 4 characters in it. And that's perfect because it has a new line in it too, isn't it? Doesn't it? Nice. So yeah, that should do it. And then we return 0. We exit with a 0 exit code. All right, so there's, I guess there's the relevant code. Let's see if it works. Oops, -o read. And so now it's waiting for my initials. My initials are LHN, and I do believe it printed them back out with that new line. Nice. And if your initials are ABC, it'll get them and print them back out. And so yeah, it reads in the ABC, and then also got the new line because you typed that as the user. So that's being read as well. It's part of the input. Okay, so that's the read syscall. And yeah, that's asking the operating system to do a fun thing for us. All right. So yeah, let's zoom out again. Let's work with main functions in assembly, and we'll write and call some functions. All right. So let's do an assembly main function that calls in assembly +1 function. So we'll write them both in assembly. And just for fun, and in our +1 function, because you can probably just do an add instruction and immediately return. To make it more interesting, we'll use like a local variable on the stack to do our +1 kind of work. All right. So here's kind of what I would like to do. I want like a main function that looks like this. This is what I want to turn into assembly. Like printf. I would like to print out an integer, and maybe like a new line at the end or something. The result of +1ing, it's my function, +1 on like the number 42 or something. And then return 0, of course. But that's kind of what I want to do. So I want to make this kind of happen. So I need to call this function first, and then I can print it. Put all the things in the proper registers. So yeah, there's my function that I'm making as well. All right. So I'll call this, I guess, +1.s. So let's steal my hello with a main function file, because that's got a lot of things I need. +1.s. paste. And so I am going to be calling some functions, so I need that around. And I do want to clean up the stack and return 0, so that's good. And I think I will need the data section, but not for that. Okay, so here's where I put my stuff. Okay, so yeah, this is kind of what I want to do. I want to make a +1 function. Let's pretend we have it. Let's call our +1 function, and then print out the answer. So it's printf. All right, so let's call +1 on 42. Let's pretend we have that function already. It's called +1. All right, so we can print that result. Okay, so move into, it's going to take an int. So w0, 42, and then we'll bl +1. And so now the answer, because it's going to return an int, is going to go in w0 again. So now w0 now holds the result. Beautiful. And we want to print that value by calling printf. So essentially what I'd like to do, if I could, was something like this. Printf, %d, new line, and then whatever's in w0. But that's not going to work, right? Because x0 is what needs this, and that clobbers w0. And this needs to be w1, right? That second argument needs to go there in w1. So let's remember that. Remember that the first 8 arguments always go in x0 through x7. And so we're going to use x0 and w1. All right, so move into w1, what's in w0, because that's where the result needs to go. And then it's going to go, and x0 needs to be the string that I'm going to use to print stuff out with. So let's call that just stir again. Stir is ASCII Z, C string, %d new line. So that's there now. And now I'm ready to BL printf. Okay. I think that's what I want to do. Yeah. And remember, the whole point of saving LR up here is because when we BL printf, we forgot where main needs to return to. So this is going to clobber LR. And sets it to be this, the address of this instruction, which is not where main itself needs to return to. It's where printf needs to return to, but not main, right? And then we'll clean up and return 0. So yeah, that's pretty much the main function. Now let's do the same for our +1 function. Let's make that in assembly, right? +1. So I'll put it down here before the data section. So this is global +1, and it's a function. And here's where it starts. And it looks like this, right? This is how you would declare it. It'd be like int +1 int x or something. And so we have our first argument in w0, right? So I know that you can implement this very, very quickly because you have to return your value in w0. Super simple, but let's make it fancier. All right, let's use the stack to do the +1 work. Let's make a local variable on the stack, all right? So let's make room on the stack to do our intermediate work. All right, so remember that SP itself stores a pointer to the top of the stack right now, and that address is in use right now unless you change it. And the stack grows downwards, so we're going to subtract. It grows down, we say. All right, towards lower addresses. And so if we would like to hold our 4 bytes of information, so to make room for 4 more bytes, I can subtract from the stack, but I need to subtract always a multiple of 16, all right? We need to make room for 4 more bytes, but every time you subtract from SP, it has to be a multiple of 16. The technical term, the reason that we're doing this is called alignment, if you want to look that up. We'll talk about it later in the class. So that's why that needs to happen. And so even though I only want to save 4 bytes, I need to subtract 16 from SP. 16. And this is just, technically I think I could subtract 4 here and nothing would go wrong, but it's better to just play by the rules always. All right. So now I have options. I can place this 4-byte thing in a lot of different places. So now we have room in SP itself. Dereference it. Got room there. SP plus 4, SP plus 8, and also SP plus 12. Those are because I just made 4 different 4-byte places in memory by subtracting 16 bytes from SP. All right. So let's just make it easy and we'll store it in just SP. All right. So yeah, that will work. So let's save our argument. Our argument was in W0, right? Let's save that on the stack. So I will store, okay? I will store what's in W0 onto the top of the stack. 4 bytes there, all right? And then for fun, I will load from the stack into some other register, all right? We're just having fun here. This is obviously overkill and unnecessary, but it's good practice. So let's load from the stack into W1, because why not? That's where our argument was. Let's do it there. Let's add, right? What I need to return is my argument plus 1. So I just got the argument back into W1 for fun. Let's add 1 to that. And then I guess I need to do what? Dun, dun, dun. Let's store back. Store the answer back, because we're having fun. Store the answer back. And so yeah, store W1 into SP again. And then our return value, right? We need to return a value. That's an int. That's x plus 1. So the answer is sitting in SP right now. Let's get it into W0. Our return value goes in W0 because it's an int. So let's load into W0. Why not? For fun. We're just going through the stack the whole time. I know we didn't need to do this. So then, all right, we have our answer in W0. We have to remember to clean up our stack before we return, because the person who we're returning to imagines that the stack is as it was before they called us. So we subbed 16 from SP. We better add 16 to SP. Boop. So now it's cleaned up. And then we're ready to ret, right? Because we never touched LR. We're good to return to whatever was there. And then we're going back to whoever called us. All right, so that's plus 1. And that will work together. Let's see if I can zoom out a lot. That will work together with the main function who's calling us. All right. So yeah, pretty much what I just drew is what happened. So let's GCC plus 1 dot s. Oh, and call it something useful. Dash o plus 1. Boop. So just like that. And in theory, this is a very complicated program that prints 43. Yay! We did it. Seems to work. All right, so that's a good silly program to study up on. And yeah, I think that was all of this example that I wanted to show you. I have to pause the recording for just a minute and go get my laundry, but I will be right back and we will continue. It will be as if nothing has happened because it's going to be paused as I record it, of course. Alright, time has passed for me, but not for you. Let's keep on trucking. So, yeah, let's next go into, like, the design of a CPU. The original design that von Neumann came up with all those years ago is still very, very much applying today. So yeah, let's talk about that architecture for a second. The von Neumann architecture, invented by a very famous man, and kind of here's the idea. It's so generic that it still applies to every single computer ever. So the idea is that you have these 5 separate pieces of your computer, and they're all connected in some way. These 2 first pieces make up the CPU. So you got a processing unit and a control unit. All right. So the processing unit is where like stuff happens. It's where you have all your registers, save all your data. It's important. Processing unit, and then you also this is also where like arithmetic is done and all those kinds of operations. So you have your little piece of pants that you know now is your ALU. If I can draw a pair of pants properly, there you go, something like that. So yeah, anything that you could want to do computation-wise happens in the processing unit, obviously. Information is processed there. And it's the control unit, though, running the show. That's the other part of the CPU. That's holding some special registers. You have PC. That's an important one. That's always the address of your current instruction. And then IR is a place where it stores that instruction for a second. It's like kind of like doing a load into there. We'll get into that more later. But yeah, that's kind of what's going on in the CPU, and everybody else is connected along buses. You got your memory, and that's very important. That's your RAM, your main memory as your program is running, and then input units and output units, and sometimes you also have input-output units. But let's just consider them to be separate, or like separate pieces of them. Okay, so yeah, all these guys are connected along these different buses, which are just wires that let you access other things, tell somebody else what to do. So the control unit is using this control bus, for example, to say, hey memory, I would like to read address 42, please. And the memory unit's like, first of all, it says, hey memory unit, I'd like to read an address, please. And then it sends the address that it wants to read along the address bus. Okay? And then the memory unit wakes up and it's like, okay, yes, I understand what you want. I will go find address 42 and send it back to you along the data bus. So that's kind of how they all talk to each other. Okay? And so they're all usually hooking into this control unit. It's like, okay, input unit, turn yourself on, or output unit, I'm about to give you some information and then I'll send it to you along the data bus or something, or take it from memory, stuff like that. So they're all talking to each other. That's kind of how you think about it. And yeah, that's the von Neumann architecture. That's how all computers look these days. You have different kinds of computers though, and they can be separated into two major categories: RISC machines and CISC machines. So RISC stands for reduced instruction set computing, or computers, and ARM processors are more or less in that camp. They got a bit more complicated recently, but they still don't have like a modulus instruction, so there's more to be looked for there. But yeah, they try to keep things simple. That's what a RISC machine is all about. Okay, that's how that works. And CISC is a different kind of architecture. Well, it's still von Neumann, but it's Intel x86 is a good example of it. You just have some giant different kinds of instructions that do fancy things that are not very basic operations. ARM is about doing a bunch of little basic operations in tandem or together to achieve your goal, and x86 is like, let's do that 50 instruction idea that you would do on ARM. Let's just have one instruction for that. Okay, so they like to add more stuff to their assembly language. That's a good way to explain it, I guess. Yeah, so in instruction set architecture, so RISC and CISC are different kinds of instruction set architectures. ARM and x86 are examples of them. All that means is just like the language that the CPU understands. It's a list of all the instructions that the architecture supports. That's what it means to be an instruction set architecture. It's like, I support this exact kind of move instruction. It's called this. It looks like this in memory. This is how it works, all right? So, like, I have this add instruction. This is what it looks like. Here's how you can use it. That's what an ISA is doing. It's listing out all the different things that the architecture supports, and also it gives the encoding of those instructions. So it's like, all right, if you see add W0, W01, that corresponds exactly to this 32-bit number, because every instruction in ARM land is 32 bits long. So like, these bytes exactly mean this. And so it's like the language that the CPU speaks. That's how you can think of an instruction set architecture. All right. And then finally, if I zoom in, memory, there's a hierarchy to it. All right. So that's very important to remember. We'll talk a bit more about certain pieces of it later. But yeah, here's the idea for now is registers, there's not very many of them, but they're very, very fast to access. You can get them in one CPU cycle. They exist on the CPU. They're very quick to get at, but they cost a lot of money to make. All right, so that's why we only have so few. So just use the ones that we have, 32 of them, ish. And then we have to spread out. If we want to store more things, we have to put it in other places that are cheaper to make, all right? And farther away from the CPU as well, all right? So yeah, eventually everything gets on a register if you want to do computation, because that is, if I scroll up to the processing unit, everything in the processing unit happens with register values. Like you shove those into the ALU and it gives you an answer back. So eventually you need to get your stuff into a register, but we don't have that many of them. So we store other things in other places. So there's a special thing called a cache, or a few of them. There are caches that store on the order of like kilobytes of information. And so that's a lot more than a register. And they're still pretty expensive, though. That's why they don't store gigabytes of information. They're closer to the CPU than like a hard drive. They are on the CPU, but farther away than registers. And they take about 10 cycles, let's say, 10 clock cycles of your CPU to go and get something out of the cache. And it has to wait during that time. So it's better to keep things in a register when you can. Otherwise, you got to like spill it over into the cache. Again, we'll talk more about this later. But then you have RAM. So RAM is important, of course. That's where everything goes when your program's running. But you do not want to be reading from main memory all day long, because it takes forever, as far as the CPU is concerned, to read something out of main memory. All right, so you can buy gigabytes of RAM these days. It's a lot cheaper than a bunch of gigabytes of register memory, but it's still not enough to hold everything, right? It takes 100 cycles, let's say, to get there. It's a little bit cheaper, but you have to pay for that in terms of access speed, okay? And then you have like your SSDs and your spinning hard drives and stuff below that. That's where you, like, it's cheaper, it's much, much farther away. It's called secondary storage at that point rather than primary storage, and it takes eons to read from, 1 million cycles, 10 million cycles to read from these guys. But you have more space, right? You have a lot more space that you can store there. And so the goal is to read from your hard drive into main memory, and then it's there and it's faster to access, all right? And then bring it into a register when you really have to do work with something in memory for a while, okay? That's kind of the goal. That's the hierarchy of memory, okay? So at the very lowest level is like something not even in your room. So like you're connected to a computer somewhere else and they have to read out of their hard drive, send it through the network, and then you get it from your network card. So that takes forever. And that just has to do with latency. You can't even put a number on that. Okay, so that takes like a century as far as the CPU is concerned. All right, so yeah, that's a little bit about computer architecture. We also talked about number systems, so you can never forget that, right? As long as you are computer scientists, we have to remember our bases in base conversion. So let's remember the easy way, right? Let's convert a number in a different base. This is a base 2 number, a binary number. Let's convert it to decimal. How do we do it? Well, we start with the rightmost digit, and that's like the 2 to the 0's place. We're going to do, all right, that's going to be 0 times 2 to the 0. Plus, okay, there's a 1 times 2 to the 1's place. Plus a 1 times 2 squared's place. And the 0's don't really contribute anything. That's like 2 to the 3rds, 2 to the 4th. Let's just care about the 1's now. 1 times 2 to the 5th. Plus dot dot dot, a bunch of 0's. Plus 1 times 2 to the 5th. Okay? So there's that. And like, what is this? This is, that's a 1. Or sorry, this is a 2. This is a 4, 2, 4, 8, 16. Then this is a 32. So it's those guys. 32 plus 4 plus 2 is 40 in decimal base 10 land that we know and love. Okay? So, yeah, there's also plenty other number systems. There's hexadecimal. Powers of 2 are good bases. Let's go in the other direction by doing the algorithm. All right, that's going to use the remainder operation modulus as well as integer division to convert to a base that you care about. So let's convert 35, the decimal number 35, to hex as well as to binary. It's fastest to convert it to hex first because you can read off the binary after that. So let's do this. So 35, how do I get the rightmost hex digit of 35? I'm going to mod by 16. All right, so 30 goes in twice to make 32 with 3 left over. So 3 is going to be the rightmost hex digit of 35. And then I want to shift away the 3 out of the decimal representation of 35 to get a smaller number that I can convert to hexadecimal and keep going with. So I'll do integer division by 16, which we decided was 2. Goes in 2 with 3 left over, right? So now if I can just convert 2 to hexadecimal, let's get its rightmost hex digit. Goes in 0 times with 2 left over. And then let's shift away that 2 to see if there's anything left. No, we're done once we get 0. And so every time we took a modulus, this guy and this guy, we got a digit in reverse order. So it's 2, 3. 2, 3 base 16 is our answer for hex, okay? And you can always check that because you can go the other way, right? You can go back the other way with this kind of expansion. It's easier. So convince yourself that that's correct. And then it's very easy to go to binary from hex because you can just take each digit in hex corresponds to 4 bits in binary. So just convert 3 to 4 bits of 3. What is that? It's going to be 0, 0, 1, 1, and then convert the 2 to 4 bits of 2, 0, 0, 1, 0. And then that is legitimately your binary answer. You can just kind of get rid of the leading zeros, of course. So the real answer is 1, 0, 0, 0, 1, 1, base 2 for binary. All right? And yeah, good practice for you would be like convert it to octal, base 8, convert it to base 5, some arbitrary base. But there is a trick if you're going in between bases that are powers of 2. All right, so remember the trick. I think that's all I wanted to say on that slide, yeah? Let me just check my notes real quick. Yep. And then finally, the last thing I want to talk about is our logic gates. So we have these 3 gates are the important ones. So you have an AND gate, an OR gate, and a NOT gate, or an inverter. The symbols that you'll see for those are AND looks like these guys. These you know from C and C++. This is like the mathematical AND operation. And then OR looks like this. Its mathematical form is that. And then NOT, bitwise negation operator, logical NOT from C or C++. And then you have this is the mathematical symbol for logical negation. Okay. So yeah, we can make circuits with these guys. So let's make a circuit for this using bitwise operators for fun, because that's what your book does. And let's make that circuit, and then we'll try to run through our circuit and see, like, when these are the input values, what is the output value, right? So 1 is true, 0 is false, 1 is high voltage, 0 is low voltage, all that fun stuff. So yeah, if I have X, Y, and Z here as my inputs, I need wires coming in from X, Y, and Z, all right? So yeah, let's do each of these pieces. Let's do X ANDed with not Y. So I got my X on a wire, I got Y on a wire, so I need to negate it to make not Y. All right, so now I got not Y coming out of here. And then I'll AND those, all right, because that was the first bit. Boop, so that's the AND gate. So there they go. And so now I have X ANDed with not Y. And then I need to do the same. I need to OR all that with Z ANDed with not X. So let's take, I got Z, cool. Let's take not X now. So let's hook in to this wire, get an X, boop, hop over the Y, and get that negated. So that's not X. And Z, that's supposed to be touching there. And then we'll feed those to their own little AND gate, right? Or it doesn't matter for AND gates. It's commutative. And so coming out of here is going to be Z ANDed with not X. Perfect. And then, like, the final answer is all that plus ORed with all that. So I'll use an OR gate. So one last time, get a little OR gate. It's hard for me to draw it. There we go. And then finally, coming out of this wire is the output that I care about. All right. So this is some important thing for us CPU makers. We needed exactly this, and now we got it. Got a wire saying exactly that. Okay. So let's, for the last example, let's figure out what the actual output is when X is true, Y is false, and Z is true. So X is, we're saying, is 1, 0, 1. So let's see what all the wires say. So we got a 1 coming in here, and then negation of 0 is a 1, right? Because we got 0 coming in, then that makes it a 1. So 1 and with 1 is still 1. And then for these guys, X negated is 0, Z is 1, but the AND of those is, of course, going to be a 0. And then we have 1 ORed with 0, true ORed with false. As long as there's a 1 somewhere, the output's going to be 1, right? So yeah, that's logic gates in a nutshell, and I think that is all that I wanted to review. So go check the other slides and all that. Check my example code from class, and also read your textbook, remember. But that is a good example, I think, of the kinds of things you'll want to know for sure on the exam. So yeah, I think that's all that I wanted to say. Yell at me, come to office hours if you have any questions about anything, and yeah, I'll see you later.